I want to move ahead with. So in today's lecture, we are going to move ahead with kinematics in 2 dimensions and 3 dimensions in general. And in particular, we are going to talk about projectile motion.
So,
yes. Yes,
so like I have some notes in major test, so you're going to discuss right now. Separate class there will be for it.
There will be a separate lecture beta for you for the discussion of the major test. But in general, also you can always send me the doubts on WhatsApp. I will help you out with that. Okay.
Oh, okay, sir.
Okay. So today we will start with projectile motion, which is an important section of kinematics. Okay. This is all still within kinematics 1. Okay. In our syllabus, we have divided kinematics into 2 parts, kinematics 1 and 2. And kinematics 1 is in your physics module number 1. Okay. Kinematics 2 has something called relative motion, which we'll be discussing after this. Okay. So this is still within kinematics 1. So within projectile motion, this will be session number 1. Okay. Now, before we get into projectile motion, let's just quickly revise the concept of the vector parameters of kinematics. When we are especially dealing with kinematics in 2 dimensions or 3 dimensions, whatever be the case. Okay. So we define our coordinate frame in general. I'll take the 3-dimensional system, then we can reduce it to 2 dimensions if required. So our reference frame becomes an XYZ coordinate system, which is the Cartesian rectangular coordinate system. So the reference frame is XYZ Cartesian coordinate frame. So Cartesian frame means the axes are mutually perpendicular to each other. And it also means that the direction of X, Y, and Z is according with the right-handed system, which you've learned in cross products, that I cap cross J cap is equal to K cap. So, that is mutually perpendicular axes such that unit vectors are related to each other like this. Okay. Now, in that, if a certain particle is located at a certain position X, Y, Z, so even though in my diagram it looks like it's in the XY plane, but just imagine that it's actually outside the XY plane. So it's having a Z coordinate also, it's outside the plane of the board. Then the first definition that we have, which we've seen earlier, is position expressed as a vector for a particle P at the point X, Y, Z. So the position vector is nothing but the vector joining the origin with the point where the particle is located. So X I cap plus Y J cap plus Z K cap. This becomes the vector notation definition of position in 3D. If it is 2-dimensional, then of course we will write it as just X I cap plus Y J cap. So accordingly, if a particle is moving from one point to another, let's say it was located over here at time t1, and after some time it's located over here at t2. So we define the displacement as the vector joining the initial position with the final position. So we can see, according to vector algebra now, that displacement becomes the difference of initial position and final position. So with respect to our coordinate frame, if at the start of a certain time interval, at time t1, if a particle was located at this position, and after some time, through whatever path it moved, it reached this other position where it is at t2. Then during that time interval t1 to t2, the displacement becomes the vector joining the initial position where the particle is located, that is this point here, to the final position. So according to vector algebra, you can see that that displacement vector S, it is the difference of the final position minus the initial position, or in general, we can say displacement is delta R. It is the change in position. Okay, so this is displacement from t equal to t1. Okay, when the position was r1, t equal to t2, when the position is r2. So in one-dimensional kinematics, we had seen, if you just do a comparison of this with 1D kinematics, that position was defined by just a coordinate. So it was a scalar notation. Displacement was therefore delta x, or S was x2 minus x1. Now in 2 and 3-dimensional kinematics, this becomes a vector notation. So the position is defined by the vector quantity R, which has all three components in general for 3-dimensional x, y, and z. And accordingly, the displacement is the vector difference of the final position minus the initial position. Okay, like that, we had seen that velocity was defined as ds by dt, or that's the same thing as dx by dt. Now, same way, we'll see velocity defined over here as a vector quantity, and acceleration was defined as dv by dt, or d2s by dt square. The same way here, it will become a vector quantity. So we are familiar with some of these things from before, but we are doing a quick revision of it because we'll be applying these concepts in projectile motion very soon. These are parts of general concepts. Then we'll come back to projectile motion. Okay, now likewise, we can see that the velocity, it is defined in two ways. One is the instantaneous velocity. That will be defined as instantaneous rate of change of position with respect to time, or instantaneous rate of change of displacement with respect to time. Okay, and if we talk about average velocity, then that will be defined as total displacement upon total time, or you can write the displacement as r2 minus r1 during a time interval of t2 minus t1. So generally we talk about instantaneous velocity only. So if we just use the term velocity alone, by default we're talking about instantaneous velocity. Whereas if you're talking about average velocity for some reason, then we always define it separately with the prefix average. Now at this stage, it might be a little bit confusing how we are going to differentiate vectors. So don't worry about that. We'll look at a couple of examples and it will become clear. But let's finish the sequence of definitions first. So the third and final definition, acceleration, displacement, and velocity. Of course, position is also there, but the important things to do with motion are displacement, velocity, and acceleration. So acceleration is rate of change of velocity with respect to time. So again, we define instantaneous acceleration as instantaneous rate of change of velocity with respect to time. And once in a while, we also need to understand the term average, though not very often. The term average acceleration. For that, we have the separate symbol A average. It is equal to delta V by delta T. That is the average rate of change of velocity with respect to time. So V2 minus V1 upon T2 minus V1. Generally, as I said, we're talking about acceleration as the instantaneous acceleration and not average acceleration. Okay, so in a sense, this is the complete set of definitions that we require in kinematics. And when we are dealing with 2 and 3-dimensional kinematics, as you can see, the definitions are based on vector relationships and not on scalars. Whereas in 1 dimension, we are reducing this to a scalar notation, like you're seeing on the side over there. Okay. So let's get used to all this notation. First of all, so I'll just leave you with a minute to go through this. In case of any doubt related to any of these parameters, just let me know. I'll explain it again. Then we will look at application example, and it will become clear how to apply these definitions in actual numerical situation. Okay, first, you just make sure you're clear with what the definition is. Okay, so people are clear with the definition.
So,
Yeah.
so what did you wrote after neutrally?
After which part?
Neutrally, sir, that reference figures.
No, it's not neutrally better. Reference frame is XYZ Cartesian coordinate frame, mutually perpendicular. Okay, that is a short form for perpendicular.
Okay.
It's mutually perpendicular. This symbol perpendicular with an R stands for. You might have seen this symbol in maths also before. So the axes, the X, Y, and Z axis are mutually perpendicular. And not only that, they should be pointing in such a direction that the direction of I cap cross J cap is equal to K cap. That means in the diagram that I've shown you, the Z axis is coming out of the plane and it's not going into the plane. So I'm sure you've discussed about that cross product concept in vectors. Okay, so let's move ahead with an application example, and then we will come straight to the topic for the day, which is projectile motion. So suppose we have a situation like this, that a particle moves in the XY plane, starting from rest at the origin, okay, at time t equal to 0, such that its coordinates are, in fact, let's do one thing, let's make this more interesting. We will not make it start at the origin, so it's just starting from rest. Okay, it's not necessary that it must start at the origin, so we'll remove that from this. Okay, so starting at time t equal to 0, such that its coordinates are given by this relation, that x is equal to 2 plus 3t, and the y coordinate is 2t square. Okay, so the coordinates are this as functions of time t. X and y are in meters, and time t is in seconds. So first of all, express its instantaneous position vector r in terms of t. Then secondly, express its instantaneous displacement s, again in terms of t. Third, calculate its displacement from t equal to 0 to t equal to 2 seconds, from 2 to 4 seconds, and 0 to 4 seconds. The next thing we'll do is we'll also calculate its instantaneous velocity v and acceleration a in terms of t. And finally, calculate its velocity and the magnitude of its velocity at the instant t equal to 2 seconds. Okay. So let's just try out this question. And with this, we will have clarity with all the definitions and the application of calculus and all that in this. So just try out this question and send me the answers in the text message, please. Okay, nobody has sent me the answers yet, so I'm hoping you people are trying the question. So let's start by understanding the position vector. The first part is very easy. You can see all you have to do is substitute x and y. So the position vector is x I cap plus y j cap, because it's a two-dimensional motion here. It's moving in the xy plane only, so there's no z coordinate. And then you have to just substitute where x is this and y is this. So you can see position as a function of time is just becoming 2 plus 3t I cap plus 2t squared j cap, where each of these components are in meters and the time is in seconds. Now, once you got this, now we talk about the displacement at some time t. So this is instantaneous position. It means position at any instant of time t equal to t. So now similarly, if you want to find out the instantaneous displacement, at time t equal to t, it is basically the displacement from the start of motion, that is at t equal to 0, to some instant of time t equal to t. Okay. So that will just become the position at time t minus the position at time 0. So position at time 0 is 2 I cap, as you can see, is the initial position. And position at time t we have already written above. So the displacement going from this initial position to this time t is the difference of these two. So it will just become 3t I cap plus 2t square j cap. So this is our instantaneous displacement at some time t. That is from the start of motion at t equal to 0 till some time t. How much displacement has happened? This is the displacement has happened. Whereas at some instant of time t, what is the position? This is the position. Okay, now just use these definitions and these two formulae that I'm going here to work out the third and fourth part yourself.
Sir, Sir,
Okay, so now all we have to do in the third part is substitute the values here. So for example, you can see that E part, we want the displacement from 0 to 2 seconds. So it's basically just the value of this instantaneous displacement at 2 seconds. Okay. So substitute the value of t as 2 seconds here. So you can see you'll get 6 I cap plus 8 j cap. Okay. You want to calculate the magnitude of this displacement,
sir,
you can see.
uh, sir, where did we find that initial position is 2 I cap?
Substitute t as 0 and r.
Oh,
In this
okay.
equation, substitute t as 0. Okay. So here, substitute t as 0. So that will give you this.
Yes, sir.
Similarly, we want to find the displacement from 2 to 4 seconds. So it should be the position at 4 seconds minus the position at 2 seconds. So position at 4 seconds will become 12 I cap plus 32 j cap, and position at 2 seconds we just seen above, it is 6 I cap plus 8 j cap. So the displacement from 2 to 4 seconds will become this. So it's 6 I cap plus 32 minus 8, that is 24 j cap. Now the C part, when you want to calculate displacement from 0 to 4 seconds, you can directly substitute in this t equal to 4 and you will get the answer. Or what we can also observe is that the displacement from 0 to 4 is actually the sum of the displacement from 0 to 2 plus the displacement from 2 to 4. So you can check that. And whatever values we've got here, if you add this displacement and this one, you will get this one. Okay. So that we completed on this. Now let's come to this one, the fourth part. So in the fourth part, you have to use the definition of instantaneous velocity as instantaneous rate of change of displacement or rate of change of velocity of position. Whichever of the two you want to use, you can use. So you can take this formula and differentiate it, or you can take this formula and differentiate it. Both will give you the same thing, which is the instantaneous velocity. And acceleration further you will get by differentiating that velocity term. Okay, people. So I'm just checking your answers. Yes, many of you have got this correct. So when you are basically calculating the velocity, you can go with either of the two definitions, ds by dt, or that's the same thing as dr by dt. So here, if you substitute ds by dt, you will want to differentiate this relation for s that we have written over here. So 3t I cap plus 2t square j cap. So now when you're doing the differentiation, just apply the standard principles of differentiation that we know, and don't worry about I cap and j cap. They're just constants. So we just treat them like we treat any constant during differentiation. So you take the differentiation operator inside, so it becomes differentiation of 3t, the whole thing into the constant unit vector I cap, plus again differentiation of 2t square, but that whole thing gets multiplied with the unit vector j cap. So I cap and j cap are treated like constants. So this becomes 3 I cap plus 4t j cap. So this is our instantaneous velocity as a function of time. And it will be in SI units because position and time were in SI units. Okay. And now you can see that instead of this, if we had used this, it would have been the same. It will give us the same answer. Logically, is the same thing actually. That's why. So this would have been whatever. What was the position? It was, I think, 2 plus 3t, right? That 2 is a constant. So when you differentiate it, it doesn't make any difference. That is why they are one and the same thing. ds by dt is one and the same thing as dr by dt. That's why we can use either of the two to describe instantaneous velocity. So whichever definition you go by, velocity is this. And once you have defined velocity, now we just need to differentiate that once more and we'll get the acceleration. So this time when you differentiate, you will see the acceleration does not have an x component because the x component of velocity is constant. So its derivative will become 0. The acceleration only has a y component, and that is also constant of 4. This term becomes 0 and this term becomes 4. So generally, we can say that the acceleration is 4 j cap in meters per second square. Okay, so I think that is what most of you have got. I can see. Okay, so you have done this correctly. Just be careful of doing the differentiation correctly. Okay, remember that differentiation of, for example, 3t is 3. Differentiation of 2t square is 2 times differentiation of t square. No? So it's 40. So this is like this. So these kind of things, like very basics of calculus, that is what we apply in kinematics. And of course, vector analysis also. Okay, so people, I hope all of you are clear with this. And now for the final part, we just had to find the value of instantaneous at what was it? T equal to second or something?
2.
2 seconds.
2 seconds.
Right. So just substitute the value of time. So we'll get it as 3 I cap plus 8 J cap. And from that, we'll get the magnitude of velocity at 2 seconds as square root of 64 plus 9, that is 73. That will be approximately 8.54 meters per second. So this is like the general concept of the various parameters in 2 and 3 dimensional kinematics, how we apply the vector definitions and relate them. Okay. Now we will move on to the specific situation of projectile motion, in which we'll be applying some of these concepts. So projectile motion is the motion of an object or a particle under the action of gravity, but when it is thrown from the ground level or from wherever, but on the surface of the earth, from a height also, slightly above the surface of the earth, but it is thrown what is called an oblique manner. That means the velocity with which we throw the object, it should not be vertical, or it should not even be horizontal. It should be having both the components, the the horizontal component as well as the vertical component. So that is called an oblique velocity. So if an object is thrown or projected like this, okay, where this is the surface of the earth, then we see that it takes a path like this because of gravity acting on it, and it eventually descends and comes and hits back the ground. So if it started like this at time t equal to 0, then at some time t, its velocity would have changed like this. At some other time, say t prime, its velocity would have changed like this. Okay, but all the time the net force acting on the body will be the same. It will be the gravitational force or the weight which is pulling it down. So projectile motion is the motion of an object or particle under the action of gravity. That is the Earth's gravity, of course. Okay. When projected, or that means thrown, with an initial velocity, which I've shown in the diagram as the vector u at time t equal to 0, which is oblique. That means it has both a vertical and a horizontal component. So in this diagram, if the initial velocity u or the projection velocity u makes an angle theta with the horizontal, yes, the acceleration will be constant throughout. I will explain that point also, Ishan, because the only force that's acting on it we are assuming is the gravitational force. Okay. So over here, u is called the projection velocity. Velocity with which we throw it at t equal to 0, it is called the projection velocity. And theta, that is the angle of the projection velocity u with respect to the horizontal. That is called the projection angle. Now I'm coming to your point, okay, about the acceleration. So the acceleration, the fact that we are treating the acceleration to be constant is with an assumption. Okay, it is assumed that no other force like air drag or wind resistance etc. act on the object during this motion other than its weight mg. So the net force acting on it is equal to mg. Therefore, the acceleration is equal to g in the vertically downward direction. Okay. So it is a uniform acceleration throughout the motion. Okay. So that is what we are studying projectile motion as. Of course, depending on the material with which the object is made, this is not always going to be the case in a practical situation. So for example, if we take an object made of high density material like a stone or a piece of a brick, okay, or a metallic object or something like that, and we throw it in conditions where there isn't extreme amount of wind. So this is going to be more or less correct because there will be some air drag and resistance acting on it, but those forces will be very small compared to the gravitational force. So we can neglect them because it's a high density material. But on the other hand, if we take something like, a ball of cotton wool, or even we take something like, like a table tennis ball, a ping pong ball, which is hollow inside. So the density of that material is very lightweight. So when we throw it in atmospheric air, its weight is very small compared to, I mean, it's not very small, but its weight is not extremely large compared to other forces like air drag and wind resistance. So in those situations, its motion will not quite be what we are studying over here, because those kind of objects will also be influenced by forces other than the weight, which is air drag and wind resistance. Okay. So what we are studying here in projectile motion is going to be limited to certain types of objects for which we can neglect these type of forces like air drag. And typically those type of objects are objects which are made of high density materials. Okay, so first just make a note of this, then we will see how to deal with this mathematically.
Sir, I might have gone disconnected for some time. Could you just show the value of V and mod V from the last question?
Okay, just let people finish writing this down, then towards the end I'll take it.
Yeah, sure.
Okay, so I'm just taking you to the previous question once, just make a note of the answer. If I have any doubt in the calculation also, let me know.
Sir, got it.
Okay.
You can scroll down.
Yeah.
Done, sir.
So 1 minute.
Yeah. So the main thing is just make sure you understand this point about, the net force being the weight. You need not write everything in detail because I'm sending you the notes anyway for each lecture. So now let's see how we will apply these concepts to understand the path, okay, and various things. So first of all, our choice of reference frame, that becomes important because without that we cannot define anything properly. So what we do in projectile motion is, in general, standard way of solving it is that we always take the origin at our point of projection. From the point from which we are throwing the object or we are projecting the object, that is selected as the origin of the coordinate frame, and y-axis is taken as the vertical and x-axis is taken as the horizontal, okay, such that whatever projection velocity you are having, that should lie in the xy plane. It should have an x component and it should have a y component, but it should not have a z component. That's how you should select your x and y axis. So t equal to 0, if the object is projected with a velocity u, the reference frame is selected such that The origin is at the point of projection. That you can say is the point from which the motion starts. And x-axis is the horizontal axis. And y-axis is the vertical axis. Is such that the projection velocity u lies in the xy plane. That means the motion will also occur in the xy plane. So now, having defined our reference frame like this, we can see that as the projectile sets off like this, once it has left contact with whoever was throwing the object, okay, it's moving through air, not in contact with anything else. So at any other time after t equal to 0, there's only one force acting on it, mg. So its acceleration will be g in the downward direction, whereas its velocity will keep changing with time. And so will its coordinates. So now the thing is, we want to solve this motion so that we can find these things like the velocity v and the coordinates x and y as functions of time. Okay. So the acceleration, which is uniform throughout the motion, because of the assumption that we've seen before, that only gravity is acting on it. So the acceleration which is uniform throughout the motion in vector form will be minus gj cap. Okay, so this emphasizes the point that there is no x component of acceleration, and the y component of acceleration is minus g because I've taken the y-axis upwards, whereas the initial velocity or the projection velocity that when we write in component form will become u cos theta I cap plus u sin theta j cap. Or we can express this in component form that u's x component is u cos theta and u's y component is u sin theta. Okay. So this vector notation is what we're going to use next to solve the motion such that we can find out. So next thing what we want to do is at time t equal to t, we want to find out what is the instantaneous velocity and what is the position r, or what are the coordinates we want to find out. So just make a note up to here and then we'll discuss further. Okay, so now to solve this, what we do is we take the path of the projectile, the motion in the XY plane, and we bifurcate it into two components. Okay, the horizontal component, that is along the x-axis, and the vertical component, that is along the y-axis. We can also use the term projection for component, like we've done in vectors. So horizontal and vertical component of projections. So along the horizontal axis, what is happening? The initial velocity at t equal to 0, it is u cos theta, and the acceleration is 0. So there is a uniform motion happening, zero acceleration. Okay. Whereas if you compare this with the vertical, at t equal to 0, the initial velocity was u sine theta upwards, so it's plus u sine theta, but the acceleration is minus g. So it's a case of uniformly accelerated motion. That uniform acceleration's value equal to minus g. So now we can see that along the x-axis, back to the horizontal component, at any time t, the instantaneous value of velocity will remain u cos theta. It remains uniform because it's unaccelerated. Okay? Whereas the x component of displacement is that uniform velocity into time. Whereas along the y-axis, you can see that at any time t, the y component of velocity will become u sine theta minus gt. So here we are using these equations, that v is equal to u plus at and s is equal to ut plus half at square, because it's a uniformly accelerated case. Whereas here we are using the case that velocity is constant, the acceleration is 0, and displacement is that constant velocity into time. So the y component of displacement will become the initial velocity, that is u sine theta into t plus half at square, so that a is minus g. So now these equations are giving me the component wise, instantaneous velocity and position. So these equations, they give me the velocity and position components, instantaneous velocity and positions components at time t. So if we combine them now, we can write it like this, that instantaneous velocity will become like this, u cos theta I cap plus u sine theta minus gt, and the instantaneous position after any time, or you can also write it as the displacement because it starts from the origin. So position, or you can write it as displacement also, is going to be given by this relation, u cos theta t is the x component and u sine theta t minus half gt square is the y component. So this is actually the first part of solving projectile motion, that given the initial projection velocity u and the angle of projection theta, how can we find an expression from which we know how to calculate velocity and position after any amount of time? At any time t, how do we find the instantaneous velocity and position? So this is the answer to that. These are the equations which give us that particular solution. So just make a note of this and make sure you understand the process for each of the components. Okay. Then we will discuss some specific terms like time of flight, then maximum height, horizontal range, etc. And we'll see everything that we solve from this point onwards. It will be by making use of these equations that we've written, the individual component equations. Those will be used to solve any and every other formula or concept that we solve in projectile motion. Okay, so I'm going to list out the important equations over here.
So can you scroll up?
Yeah, I'll come back to that. Okay, come back to that. But when we are doing application questions, this is how we should visualize a problem. So if we have projected something at u at an angle theta to the horizontal at time t equal to 0, and we want to find in its path when it reaches some position here or even on its way down, whatever, the velocity and the coordinates, then the most important equations are these. X coordinate is given by this, y coordinate is given by this, and x component of velocity is constant, y component of velocity is having that uniform acceleration of minus g. So it's like this. So these four equations are basically everything that we need to solve projectile motion. Okay, there are few formulas and other things also, we'll come to those, but you will see that anything that we are logically trying to solve, we can always solve from the basics by using these four equations. So these are position, at time t, and these give the individual components of the velocity at time t.
Done, sir.
Right, so now this numerical problem before we come to the formulae of range and all those things. Okay. So we'll just learn to apply this concept here. So a particle is projected at a speed of, let's say, 60 meters per second at an angle of 60 degrees with respect to the horizontal. Okay. Take the value of g as 10 meters per second square. So find its velocity v and displacement s. So this is projected at time t equal to 0. Okay, so you start your stopwatch when you throw it at this velocity at this angle. So you want to find the velocity and displacement at t equal to, oh just a minute, we'll make this 30 degrees. It will be somewhat easier to solve. Yeah, so we'll make this 30 degrees. So we'll solve this at time t equal to 2 seconds. Then once again time t equal to 3 seconds. And once again time t equal to 4 seconds. Okay, so everything you need to solve is above there in those equations which I've written. Just you have to learn how to apply those. That's how we do. Okay. I will answer your question about distance and displacement, Ishant, in just a moment. Okay. Obviously, you can see distance and displacement are not the same because it's not a straight line path. Okay. But anyway, before that, all the answers you people have sent, you can, yeah, you can just send in vector form only in I cap, J cap. You don't need to calculate the magnitudes. Okay. So you can see that from this information that is given, you can see that the initial velocity is x component is how much? It is 30 root 3 meters per second. And the y component is 30 meters per second. And g is 10 meters per second square. So from this, we can see that in general, our x coordinate as a function of time will be 30 root 3 t. And our y coordinate as a function of time will be 30 t minus 5t square. And our x component of velocity will remain constant at 30 root 3. And our y component of velocity will be varying with time, like this. So now we can substitute these for each of these parts. So at t equal to 2 seconds, you can see that the x coordinate will be 60 root 3 and the y coordinate will be how much now? It will be 60 minus 20. So it will be 40. So the position or displacement will be 60 root 3 I cap plus 40 J cap. Okay. And the velocity's x component will remain constant at 30 root 3, whereas the y component at 2 seconds will become 10. So the velocity vector will become 30 root 3 I cap plus 10 J cap in meters per second. This is in meters. And likewise, you can see for each of the parts. So like for B part, at t equal to 3 seconds, you can see something very interesting. Your velocity will only have horizontal component, whereas this will be 45 J cap. Okay. And again at t equal to 4 seconds, so your position will become but back to 40 J cap. Okay. And your velocity if you notice that between 2 seconds and 4 seconds, there's a kind of a symmetry. The y coordinates are the same, and the y component of velocity is like, you know, reverse of each other. So it's happening because it's symmetrical with respect to the ascent and descent of the projectile. So if we're starting from at t equal to 0, what you'll observe here is that if it's reached somewhere here at t equal to 2 seconds, then it's somewhere over here at t equal to 4 seconds, because they're both having the same vertical coordinate of 40 meters. They're having the same magnitude of velocity, but like this. And just the midpoint of these two is 3 seconds when it's reached this position where the velocity is becoming horizontal. And the height has become 45 meters. Okay. So to come back to your question, Ishan, distance and displacement are not the same thing in projectile motion, because for example, between 0 and 2 seconds, what is the displacement? It is the straight line joining this and this. This is the displacement vector. Whereas the distance traveled is this curved path. So it's definitely longer. Okay, so in projectile motion, it has a curved path. Okay. So that means distance in general is going to be greater than magnitude of displacement. It's only when the path is a straight line and the particle does not turn back in that straight line, it continues in the same direction directly from one point to another along a straight line. Only in that case, the distance becomes equal to magnitude of displacement. Hope this point is clear, Ishan. Okay. So in each of these cases, the position or displacement is in meters and the velocity is in meters per second. Okay.
Sir, here also at maximum point, velocity will become 0.
No, the vertical component will become 0 at the maximum height. So that's what you're seeing is happening at 3 seconds. Huh? At 3 seconds, see what is happening. The vertical component of velocity is 0. So that's how we know that it's reached the highest point in the path. That's why I've labeled that point 45 meters at the peak point. Understood, no?
Yes, sir.
But at the same time, in the horizontal direction, it's continuing to go at this thing. How we calculated V beta? So you see, we are using the formula for Vx and Vy. No? So what is the formula for Vx? It remains constant. It is equal to Ux or U cos theta. Whereas what is Vy? It is Uy minus Gt, or it is U sin theta minus Gt. So just substituting these values, and that's how we are getting these two formulae for the x and y component. Then the velocity at any instant is just equal to the x component I cap plus the y component j cap. So for example, at t equal to 10 seconds, I've got the Vx and Vy, and then I'm just converting it into a vector, unit vector notation. Okay, is it clear how you got the velocity vectors? Yes.
So,
Yes.
so the formula which you give for U is 4 sin theta minus GT, right?
Is u sin theta minus gt. Uy का value क्या है? U sin theta ना?
Oh yeah, U sin theta minus GT.
U sin theta minus. So in this case, the value of u sin theta is how much? It's 30 meters per second. So that's how we are getting, and g is 10. So that's how we are getting Uy as 30 minus 10t.
Okay, so got it. So I can just scroll up.
What was the question? You wanted me to scroll up, is it?
Yes, sir.
Okay. Tell me which part. Huh?
Yeah,
Here?
only the question part only, sir.
Okay.
The example thing.
Okay, so is this done now?
Just
Okay.
done.
Okay. Okay, now we come to three very important terms in projectile motion, and linked to them are three important formulae. Okay. And that is the maximum height that the projectile reaches, and the distance of the point at which it lands. And remember, here we're talking about a standard projectile motion, so it has to land on the same horizontal plane. Of course, you can have a variation of projectile motion where you throw it from the top of a building or from some heighted position, so it lands on the ground below. So that will be a variation situation. Okay, but here we are talking about standard projectile motion, so it has to come back to ground to the same horizontal level from which it was projected. So the distance of the point where it lands from the starting point, that is called the horizontal range. And on the way to reaching that point, it initially ascends for some time, that is, its height increases, and then eventually it descends. So the maximum height it reaches, that is a third parameter which is going to be important. So if it lands on the ground at some time capital T over here, okay, and wherever it lands, the x coordinate becomes what we call the range, and the y coordinate becomes 0. Whereas in between, it reaches a maximum height at some position, and where it reaches the maximum height, at that point of time, the velocity will become horizontal. Because if the y coordinate is reaching the maxima, okay, the dy by dt or vertical component of velocity should be 0. And we'll see that by symmetry, the time will also be half the total time. So all this is easy to understand from the four fundamental equations that we see. So first of all, here, capital T is called the total time of flight. That is the time from the projection or the start of the motion at t equal to 0 till impact on the horizontal surface. At t equal to t, capital T. Then the next important parameter is the horizontal range, for which we use the symbol capital R. So that you can say is, it's basically the displacement from t equal to 0 to capital T. Or we simply call it the range. So that is the displacement, the horizontal displacement you can see from the point of projection to the point of impact. And the third thing here is h, which is the maximum height from the horizontal level. So we will see that all these three important parameters, they depend on the projection speed u and the angle of projection theta. And their values can be calculated by making use of the four fundamental equations that we discussed earlier. Okay, so now let's see how we'll get the formula for each of these. Yes, I'll explain that point, Adinath. Okay. So first, let's revisit our equations. So x is u cos theta t. That's our equation 1. And y is u sin theta t minus half dt square. And dx at any point of time is u cos theta, whereas the y component of velocity at any point of time is u sin theta minus gt. So you'll see that we'll use a combination of these four equations. Now, first of all, see that at time t equal to capital T, total time of flight, the y coordinate is becoming how much? 0, because it returns the horizontal plane, which in our case we have taken as the x-axis. So its y coordinate should be 0. So from equation 2, you can see that u sin theta into capital T minus half gt square should be 0. So this will give us the formula for the time of flight. I'm just factorizing this. Now one root is 0, which we will not take because that's the initial time. The second root is the one which we will take, 2u sin theta by g. So this becomes our first important formula. The time of flight is 2u sin theta by g. Okay. Now, again, we can see that at that time only, the x coordinate is equal to the horizontal range. So therefore, from equation 1, you can see that the range is equal to u cos theta multiplied by capital T. Now we'll substitute this capital T here. That will give us the range. And we'll solve this one step further. And we'll get the formula that the range is u square sine 2 theta divided by g. This formula becomes the formula for the range. Of course, here we are using the identity that sine 2 theta is sine theta cos theta. So above, when you multiply, you can see you get u square into sine into 2 sine theta cos theta. So we are making use of that identity. So this is the second of the three formulae. Note this down, and then I'll explain to you the final point of the maximum height and how to calculate that, as well as how to justify the fact that at the highest point, Vy will be 0. That's why the velocity becomes u cos theta along the x-axis. And the time also is half the total time.
So,
Yes.
so here R is resultant, right?
No, R is the range, beta. We've written down the definition above. No? R is the horizontal range. Got it now?
Okay, okay.
It is the displacement along the horizontal axis where the particle is landing. See, this one is the range. Okay, so effectively this distance from here to here, this is the range. From your point of projection till here,
Okay, sir.
that is the range. Okay, and h is the maximum height. Okay, so now coming to the maximum height, the last part. So at y equal to h, that is maximum height position. Okay, dy by dt should be 0, no? Because y has reached its local maxima. You understood the point? No? At maxima, derivative is equal to 0. No? So that is the logic that the y component of velocity should be 0. Okay, so therefore our velocity should become just u cos theta I cap at the maximum height position. Okay. So now we have from our equation number 4, Vy is equal to u sine theta minus gt. So therefore at y equal to h, Vy is 0 means that u sine theta minus gt should be 0. So the time should be equal to u sine theta divided by g, which by the way, if you compare with capital T above, you can see it's half the total time. Okay. So this is the logic of the argument that when it reaches the highest point, the velocity should become horizontal. At the highest point, the instantaneous velocity v is horizontal because the vertical component is 0. And when we put that in the equation, you can see that it comes out to be half the total time of flight. So there is that symmetry in time, that half the journey is in ascent and half the journey is descent. So from t equal to 0 to t by 2, the y coordinate is going from 0 to maximum height. It's ascending. And then the second half of the journey, the y coordinate descends from h to 0. And now to get the maximum height, we just need to substitute in equation 3, y is equal to h at t equal to t by 2 or u sine theta by g. The third equation was this, that y is u sine theta t minus half gt square. So in this, substitute the value of y as h for the time being how much? The time being u sine theta by g. So that will give us the formula for the maximum height. So half gt square will become half g into u sine theta by g whole square. So Adinath, hope this point is clear now, that how come we get the idea that, at the highest point, the velocity should be u cos theta and the time should be capital T by 2. Okay, so final step, we just solve this now. So you can see that you can take u square sine square theta by g common. And from the first term, you'll have 1. From the second term, you'll have minus half. So the formula for maximum height becomes this. So these three formulae become very important for us in projectile motion. The time of flight is 2u sine theta by g. The horizontal range is u square sine 2 theta divided by g. And the maximum height it reaches is u square sine square theta divided by 2g. Okay. Apart from the 4 equations which I've shown you earlier, okay, which are used for solving anything else, but these 3 quantities directly come from these formulae. So you can see how they depend on u and theta, the projection speed and the angle of projection. Okay. So with that, we conclude today's lecture, the first lecture related to projectile motion. So next lecture, we will keep aside some time for doubts and questions from one-dimensional motion, as well as we'll discuss some questions of projectile motion, and then only we'll move forward ahead of this. Okay. So that's it for today's class. Thanks for attending, people. Wish you all the best.
Thank you.
Thank you, sir. Bye,
Thank you,
sir.
sir.
Bye.
Thank you, sir. Bye.